Okay, so in the previous class, we reviewed Ampere's law, in previous recitation class, but we haven't finished this example, right? So where we have what? We have an infinitely long straight wire. Okay, this is basically a cross section. I can try to draw a three-dimensional situation, right, like this, by adding these two lines. And current I flows through this system. Okay, I, right? And that current is uniformly distributed over the wire. And there is a hole in the wire at the center, concentric hole, right, with the radius B. Radius of the wire is A, right? So A, B, and I are given. So this is problem 57, but in that problem, instead of A and B, R1 and R2 is given. But I was just lazy to write subscripts also, R capital, subscript, it's kind of more to write, so I switched to A and B, right? So, and we need to find magnetic field everywhere in the region 1, outside. Okay, let me start labeling it region 1. Then region 2 will be in the metal, so it's a conductor, right? Since we have a current, there must be a conductor. And region 3 in the hole. So region 3. So we need to find magnetic fields in all these three regions. Again, now we have two ways of finding magnetic field of any electrical system, right? You can use either Biot-Savart law, right, or Ampere's law. They are both equally strong, right? Usage of Biot-Savart law here, it's not the easiest approach, right? So I would never recommend, right? So it's better to use Ampere's law because of the nice cylindrical symmetry in the distribution of current. Application of Ampere's law, it's a piece of cake here, right? So let's do it. Right. Yeah, as I said, let's start with region number 1. Let me put 1, circle it. And of course, since it's based on Ampere's law. Again, guys, if something not clear, you can ask me at any moment, right? Say something. So integral of the closed loop B dot ds equals to mu naught times I enclosed. And again, as I keep saying, so what should be the first step before you start applying Ampere's law? You need to pick an Amperian loop, because without that you wouldn't be able to evaluate the integral, because you need to evaluate it over a certain loop. And you will never be able to tell which current is enclosed, because then since the loop is not chosen, you cannot say which currents are enclosed and which are not. Okay, so since we're interested in the magnetic field outside, a loop must be there. Again, as I told you already multiple times, you can pick any Amperian loop your soul desires, but of course you have to be smart and you need to pick the best one so you can use the symmetry. Right, so as a result, you will be able to solve the problem, because you can pick a complicated loop, and then you will never, you will be correct, but you will never be able to solve the problem, right? So what's the point of being correct? So the best loop is a circle centered on the wire. Okay, so let me draw it. So that's an Amperian loop for part 1 with an arbitrary radius r. So then, next step, we haven't done with an Amperian loop. We have to pick a direction for integration, right? Because whenever you integrate the integral like this, you can integrate either this way, move that way, or this way, clockwise or counterclockwise, right? Since we have only one current, and you remember, direction of this direction will this direction determines direction of the this direction determines the sign of the current, right? So so we can make that current positive or we can make it negative. But of course, who wants to deal with a negative current? And of course, that current will be negative if you pick which direction? To this one. So if you pick clockwise direction, then that current will be negative. Why? Because you remember the right-hand rule number 2 applied sort of in the reverse direction. If you curl your fingers in the direction, then your outstretched thumb gives you positive direction for a current. And in this case, positive will be sort of into the board or that way, a three-dimensional picture. But I don't want to deal with the negative current. I want to have it positive. So in order to make it positive, I will pick this direction, which is counterclockwise. So if I curl my fingers this way, of course, my thumb gives me positive direction for a current. So making our current positive. So I will pick a counterclockwise direction. Right. Okay, so our current will be positive in this case. So once we're done with that, with Amperian loop, probably I should label it. Of course, it's an Amperian loop. Amp loop, right? Okay. Now we can handle this integral. So integral over the closed loop b dot ds. And again, let's show direction of ds and direction of b on the picture in order to make the first step. Direction of ds, basically, once we choose a direction of the loop, so we can show easily direction of ds. So this will be ds over here, or I can draw it where else. Okay, let me draw it here, for example, ds, or any other point. Then what about b? We justified direction of b in the lecture. So in this case, it will be tangent to the Amperian loop, to this circle centered on the wire, right? So this will be direction of b, direction of b. So, and you can pick any point in direction of ds and direction of b. They are parallel to each other, right? So the angle between them is 0. So as a result, of course, I can simplify this expression. So since b is parallel to ds, so b dot ds equals to, wrong line, it will be the equal to just the product of magnitudes, again, because the angle between these two vectors is 0. Cosine of 0 degrees is 1. Right? Okay, so now I can rewrite my integral. So it will be integral over the closed loop, b ds. And again, these are just magnitudes of both vectors. Now, the second explanation and the second step in this evaluation. If you look at distribution of current, for example, from this point on the Amperian loop, and of course, that distribution of current gives us the strength of this magnetic field, this magnitude, strength of the magnetic field. Right? So if you remember it, so now if you move yourself, for example, to this point, look at the distribution of current, it will be exactly the same. So it means that magnitude of the magnetic field will be here and here the same. Or you can move to this point or any other point and look at the distribution of current, it will be exactly the same. You will never be able to see the difference between the distribution of currents if you move yourself along this Amperian loop. So it means what? It means that the magnitude of the magnetic field will be exactly the same at any point on the Amperian loop. Of course, if you step away from the Amperian loop, for example, closer to the wire, of course, magnetic field gets stronger. If you step away, of course, the magnetic field gets weaker. But since we picked the best Amperian loop, so we can use this beauty, we can use the symmetry of the problem. So on this Amperian loop, we can say, yeah, B is constant. But if you picked, for example, an ellipse, it will be correct in terms of application of the Ampere's law. But this you wouldn't be able to tell this statement, because on the ellipse, any points of the ellipse are at different distances from the center of the wire, and distribution of currents are going to be different. Right. All right, so now I can write, so since B is constant, and again, it's not uniform, it's constant. Constant on the circle only. Constant on the Amperian loop. Right? So if it's constant, of course, we can extract it from the sign of integration, because any constant in the integral can be extracted from the sign of integration. Right. So it will be equal b and integral over the closed loop ds. And now the same question like I've asked already many times. So what's the value of this integral? in order to give the answer, we just need to know the meaning of this integral. It's just a ds plus ds plus ds plus ds plus, and you keep moving around this loop, adding these small ds's. ds is just a small length, right? So when you complete adding, when you get back to the starting point, of course you will get circumference of that circle, which is 2 pi r small. So it will be equal to b times 2 pi r. Okay, so that's the value of the integral, and it must be equal from the other side to mu naught times I enclosed. Mu naught times I enclosed, right? So now that's what we're getting from the Ampere's law, and now in order to find magnetic field, we need to find I enclosed, right? I enclosed. In this case, I enclosed, again, it's a total amount of current physically embraced by our Amperian loop. Look, Amperian loop embraces the whole wire. The whole wire is inside of our Amperian loop, right? So I enclosed is what? The total current I, right? In this case, just the total current I. So in this case, it's quite simple finding enclosed current. So from here, we can immediately solve it for B, because now we know the current, and I can write the answer immediately. So B in the region 1 as a function of R equals, this is Rome 1, right? Mu naught I divided by 2 pi R. Mu naught times I divided by 2 pi R small. But of course, that's only in the region 1. So let me frame it. It's worth of framing since it's the final result in the region 1. So now region 2. Again, if something not clear, say something, right? So now I will put Roman 2, right? So region number 2, now we are in the metal, in the wire. Of course, now a different region, of course, we need to pick a new Amperian loop. And again, in order to use the symmetry of the problem, we need to pick a circle. Right? Again, you can pick any surface, any loop you want, but most likely you will never be able to solve. So we'll pick the best one, which is the circle centered on the wire. Let me show that this is R for the second region. And steps which we made over here to evaluate this integral will be exactly the same. So it will be again I will pick the same direction, right? So it will be the same direction over here, right? So I can draw, for example, here, that's my ds. Magnetic field will be again the same direction, so B. Right? And again, I pick that direction for an integration, again, in order to make that current positive. Right? So I will write, so integral of B dot ds, and I will open my explanation box, exactly the same. Exactly the same. And I will write as a result, so it will be B times 2 pi R, right? Steps exactly the same. And equals to mu naught times I enclosed. And again, now in order to find B in the second region, we need to know I enclosed. Okay, now the part where tons and tons of mistakes, usually on the exam or tests, right? Different forms of tests, right? Maybe quizzes. But it's all about this formula, nothing else. A definition of current density. Okay, let me even frame it. J equals current density equals, take a current and divide it by a cross-sectional area through which this current flows. That's what you need to know. The rest is geometry, and that's it. So all the speculations are over here, right? All the physics is over here, right? And of course, current can be found by multiplying current density and the area. Okay, anyway, so let me find this current density first using the total current and then using enclosed current, right? So where is the enclosed current? Let's show it on the diagram, right? Basically, it's all current physically impressed by the Amperian loop. Amperian loop is over here. So pretty much it's this current flowing through this cross-sectional area, basically between B and that R small. Okay, let me highlight it with blue. It's there, right? That's our I enclosed, okay? So, yeah, as I said, let me just find, and okay, let me start with first current density using the total current. So again, using this formula, total current divided by the cross-sectional area through which the total current flows. Total current flows between what? Between a circle with radius B and the circle with radius A. So in this area, right? So we need to subtract the area of the hole. So it will be total current I divided by area with radius what? A small minus area with B small. If it's confusing, let me draw a diagram explaining why this is correct, right? So look, we're trying to find this area with a hole, right? And that is, okay, that is area with radius A minus area with radius B. So, of course, we can find this which way? You take the total area with radius A and subtract the whole, which is area with radius B. So, A sub A minus A sub B, area of the circle with radius A minus area of the circle with radius B, right? Okay, maybe let me write explicitly. I divided by what is area of the circle? Pi r squared. But of course, in this case, it's a pi a squared minus b squared. And never write a minus b squared. It's completely wrong because we're subtracting areas. We're not subtracting radii and squaring that difference. No, it's completely physically, it doesn't make sense, right? And of course, you know that the difference of squares is not equals to the square of differences. Yeah. So that's from one side. We can find current density using the total current. But from the other side, how else can we find current density? Using I enclosed. Right, again, the same formula, but now we have to use I enclosed and divided it by what? By the area through which that I enclosed flows. By this area highlighted by this blue, right? Again, we can use the same, but now instead of A sub A, we will use A sub R because now the outer radius is R small. Inner radius still the same, B. Right, so it will be A sub R minus A sub B. So it will be A sub R small minus A sub B. Right, so you see all the time we're subtracting the whole because there's no current over there. So it will be I enclosed divided by pi r squared minus b squared. And of course, these two current densities are the same because we have uniform distribution of current. It means it doesn't matter where you calculate current density, it will be exactly the same. So we calculated it using I enclosed and we calculated it using the total current. So this current density and that current densities are the same. So we can equate this with that. And as a result, we can get, this is given, we just need to find I enclosed. So I enclosed will be equal, pi gets cancelled, you see pi here, pi there. So as a result, we will get I total current and divided by this will go up here, this denominator goes up here. It will be R squared minus B squared divided by A squared minus B squared. So that's the value, that's the expression for the current enclosed by our Amperian loop. Again, it's all about this formula, but every time I'm confused, right? So why students are struggling with finding that, right? Lots of mistakes at this point, right? Okay, so now we need to plug it here and solve it for B. Okay, let me show with green. So now we just plug it over here and solve it for B. All right, so as a result, yeah, let me write. So it will be B times 2 pi R. I'm just rewriting Ampere's law, this, what we got from the Ampere's law. Equals to mu naught times I, and this R squared minus B squared divided by A squared minus B squared. Okay, 2 pi R will be moved to the right hand side, and it will go into the denominator, and we will get as a result B in the second region will be equal mu naught times I divided by 2 pi R, and that ratio of these squares, R squared minus B squared divided by A squared minus B to the power of 2. So that's the answer. That's how magnetic field changes inside of the wire. Of course, with R small, so variable is R here and there R, right? R squared. Okay, so region 2, now region number 3. Let's find it's in the third region. Again, in exactly the same way, I can say that it's all the steps are the same, so I will just write immediately this part. Right. So it will be B times 2 pi R equals to mu naught times I enclosed. And what's the value of I enclosed? At this point, everyone should be able to tell me immediately, right? And I'm sure that most of you can tell me immediately. Yeah, yeah. First of all, of course, I need to show an Amperian loop, right? Otherwise, my question is completely stupid, right? So that will be our Amperian loop, of course, inside of the wire. Probably it's difficult for you to see, but you understand it. Of course, it will be a circle after all these explanations, right? This is trivial. Right. You can pick direction, any direction, clockwise, counterclockwise for that Amperian loop, right? Because we are in the hole. It's a vacuum. There's no conductor over there, conducting material. So of course current cannot flow there. There's no current, any current. So I enclosed is 0. Right? So I enclosed is 0. So if this is 0, then magnetic field must be 0, right? So then as a result, B in the third region equals to 0. Right. Okay, wrong color. It should be red. It should be framed like this. Okay, so that's the problem. Again, in the lecture, we solved the problem when we did not have a hole in the wire. Now here we solved it with a hole. And then in the recitation classes, I looked at the next level of complexity. I added a small wire with the current in that hole, right? So as a result, we had the tube basically with the current, and at the center there was a wire with an additional current flowing in the opposite direction. So all these problems like 3 stages in making situation more and more complicated. Okay, so that's what the first problem which I wanted to discuss. Actually, I was planning to discuss it in the previous recitation class, but we ran out of time. So now, yeah, if you need something, if you have questions, you can ask. Otherwise, I will move to the next problem. 29, 22. If you're afraid to ask something during the class, right, you can come to an office hour, actually today from 2 to 3, right? You can ask it there. So what is given? It's more like a conceptual question, right, this one. And very similar to this question we discussed in our lecture as a clicker question. So we have 3 currents, I1, 2 amps, and it flows into the board, cross. It means away from you. I2 is also given 6 amps out of the board. And I3, we only know its direction, but we don't know its value. So we need to find the value of I3. Then somebody was nice enough to pick an Amperian loop. Also picked a direction, you see, clockwise direction, and calculated the value of this integral b dot ds. So somebody calculated integral of b dot ds equals to, okay, let me grab my notes. It's 3.77 times 10 to the power of minus 6. Actually, what are the units? Let's say I want here to write the units. Get just in the expression for the integral. So what we have? B, it's a Tesla. ds, it's a short, small length, meters. Tesla times meters. Again, integration is just adding exactly the same b dot ds, b dot ds, and b dot ds. We just keep adding exactly the same terms. So units will be Tesla times meters. Tesla times meters. And knowing this, we need to find I3. Go. Everything is flying. Okay. So we need to find I3. Right. Okay, direct application of Ampere's law. And the left-hand side is given. So it will be, okay, let me rewrite Ampere's law. B dot ds equals mu naught times I enclosed. So now the left-hand side is given. Left-hand side is given. Minus 6 Tesla times meters equals to mu naught times. Okay. Now we need to apply a right-hand rule in order to write all those currents with a proper sign. And again, all the currents are enclosed. So none of them is outside of the Amperian loop. If some currents were outside, of course, we would just ignore them, right? We would forget about them. But in this case, all are enclosed, right? So we will have to write them all, I1, I2, and I3. Which of them are positive and which are negative? So right-hand rule, curl your fingers in the direction, and your outstretched thumb gives you a direction, positive direction for a current. So into the board, positive direction. So it means that I1 positive, I2 negative because it's outside, and I3 also positive. So I can write I1 positive minus I2 plus I3. Everything is given except for unknown I3, right? So this is given. Mu naught, of course, we know. I1 is also given. I2 is given. So we just need to solve it for I3. Piece of cake, right? Okay, I'm not going to plug numbers. I will just write down the answer. So from here, I3 equals to, where the answer, 7 amps. 7 amps of current. Right. Okay, so because it's sort of algebra is so simple, analysis is reasonably simple, right? So this type of questions I asked a few times in the past among multiple choice questions. Right? Okay. Again, usually don't have significant problems with a problem of this type. Okay, now enough of Ampere's law, right? Now let's look at the next problem. So this class, again, I dedicate completely to finding magnetic fields because in the lecture, I haven't started introducing magnetic force. So tomorrow I will start doing this and we will start solving problems about finding magnetic force. But for now, just all about magnetic field production. Right? So next problem is 2912. 2912. Okay, so now I need to draw a nice picture. And probably I will start with a coordinate system, with a coordinate system, because then the rest of the picture will be easier to draw. And I think finally I can start using my ruler. So I think it should be enough space over here. So let's say this is x-axis. This will be my y-axis. Should be enough. Right. So y in centimeters, x is in centimeters as well. And we have two currents, infinitely long currents, parallel to each other. Sort of like this. One current will flow out of the board and one current into the board. Right, sort of like this. But infinitely long straight wires with current. But of course currents, but currents in opposite directions. Right. So the first current is, you know what, let me try to estimate where I should position that point. Okay, probably here somewhere. You will understand why I'm using this ruler in order to get position it at a nice spot, right? So let's say this will be a place for the current 1. It's at point 1 and 1. Okay, so now let me draw that current. So this current flows out of the board. So it's I1 equals to 10 amps. 10 amps, yeah. Second current will be symmetrically positioned, again, symmetrically relative to x-axis. Right, so it means that it should be, this is 1, this should be -1. Right. So it will be at that point. And this current is out of the, no, into the board, So this is I2 equals to also 10 amps. So we need to find magnetic field, net magnetic field at the origin, point O. Okay, let me draw a few auxiliary lines immediately. This one, all right, this one, right. And let me label points. So this is O, this is A, let's say this is B, and intersection with the x-axis C. O, A, B, and C. Right. Okay. That's what is given, right? And we need to find magnetic field at O. So let me write down. So find B at O. So in terms of physics, first, physics is it's reasonably simple. This infinitely long straight wire creates its own magnetic field, and of course, the whole space will be filled with that magnetic field. And of course, we know how we can find the magnitude of that magnetic field. It will be something like this: mu naught I divided by 2 pi r, right? Where r is the perpendicular, the shortest distance between the wire and the point in question. Then this current creates its own magnetic field independently from the first one, and again we can find the magnitude and direction of this magnetic field easily, right? Okay, so point is given. So let's just draw first properly magnetic field B1 and magnetic field B2, right? With the proper direction. And you know what? In order to draw nicely B1 and B2, let me draw magnetic field lines. And you remember magnetic field lines of an infinitely straight wire. How can we find it? Outstretch your thumb in the direction of the current and curl your fingers around the wire. Right? So we're going to apply it twice, for the first wire and for the second. Okay, let me draw that. Let me start with the first one. All right, and now I can use these again, since the circular has a circular shape. All right. Right. It will be something like this. You see, it goes through the point in question, right? And centered on the wire. So I can draw this greenish magnetic field line. It's one of the magnetic field lines, right? Of course, we can draw as many as you want, but we just need only one in this case. And what's the direction? Again, right-hand rule. So outstretch my thumb in the direction of the current and my fingers. Okay, probably I should do it like this. And my fingers, curl fingers, gives me this direction, which is counterclockwise. Right. And immediately we can draw magnetic field relative to this magnetic field line. So you remember what's the direction of the magnetic field? How can we get it based on the magnetic field lines? Magnetic field is tangent to the magnetic field line, right? Tangent at this point. Okay, let me draw it. And first, without justifying, I will draw it in the correct direction, and in a second I will justify it. So magnetic field, I claim, will lie along this line between O and B. I claim, but I will prove it in a second, that magnetic field lies on the line connecting point O and B. So that is my B1. Okay, now let me prove it, that this is the correct direction for B1. Look, what can you say about this line from A to O relative to this circle, which is the magnetic field? It's the radial direction, because this is the center of that circle, right? So this is the radial direction to the circle. Basically, it's sort of like a radius, right? So radial direction. What about B direction? By definition, you remember, it's a tangential direction. Magnetic field is tangent to the circle. So this is radial direction, this is tangential direction. What's the angle between the radial and tangential direction? 90 degrees. So this angle is 90 degrees. All right? Then, second, what can you say about this angle between this radial direction and x-axis? It's a 45 degrees, because this is 1, so this angle is 45 degrees. If this whole angle is 90 degrees and this is 45 degrees, then what's this angle? 45 degrees. So it means that direction of magnetic field will lie along this line OB. because that line is at 45 degrees as well, because this angle is 45, right? So that's the proof. Of course, I'm not going to write it because it will take me like 5 minutes just writing what I just told you, but it's quite reasonable. Again, this is radial direction, this is tangential direction. So this is 90 degrees. And since we see that this is 45 degrees, it means that this angle between B and the x-axis must be 45 degrees as well, right? So it means that B1 lies on this line OB, right? Okay, now let's repeat exactly the same, but now for the magnetic field created by the second wire, I2. Again, let me grab my ruler, right, and draw everything, but now in blue. All right, so this will be my magnetic field line. Enough. All right, direction, right-hand rule. Current is into the board, so my thumb is into the board, and this will be our direction. So which is clockwise. Right? And now, of course, we need to draw magnetic field, which is again tangent to the magnetic field line. So it means, okay, there's something wrong with the power. Okay, this is direction of B2, right? So now we have B1 and B2. We will show in a second that magnitudes of these two vectors are going to be the same. Why? Because current 10 amps, current 10 amps. This distance and that distance are the same. We will show it mathematically in a second, right? So most likely B1, magnitude of B1 equals to the magnitude of B2, right? So pretty much after this, we will have to just add them as vectors. And how I'm going to do it? First, I will find the magnitude of B1. Then I can find x component of B1 and y component of B1. Then, second step, I will find magnitude of B2 and find components, x component of B2 and y component of B2. Then we will have two vectors presented in a component form, and then we can easily add them up. Do you remember? We've used this approach twice at the beginning of the semester when we tried to find the net electric field. But now, magnetic field. But the steps, the same. First magnitude, then x component, y component. Magnitude, x component, y component, and then add corresponding components. So that's what I'm going to apply here, right? Okay, so now let's start with B1, right? So B1, it's a magnitude of B1, right? You see, magnitude of B1. How can we find that? The formula which we derived in the lecture, which is similar to this mu naught I divided by 2 pi r. Right, so it will be mu naught times I1 divided by 2 pi r1. What is r1? It's the shortest distance from the wire to the point where we want to find magnetic field. This is I1, this is the point. So we're talking about this distance OA, which we can easily find using Pythagorean theorem, because this distance is given, it's 1 centimeter. This distance is also given, 1 centimeter. So we'll get square root of 2. So let me emphasize on that. So R1 equals to, it's a OA, and of course it will be square root of 1 centimeters squared plus 1 centimeters squared. So that will be equal to square root of 2. But of course, at some point, we will have to convert into meters. So let me do it at this point. So it will be square root of 2 times 10 to the power of minus 2 meters. Right? So R1 equal, and of course you can plug it there. You can find the magnitude because everything is given. Current is given, mu naught you know, R1 we found. So now let's find components. Okay, 5 minutes, we still have time to finish. So components. In order to find components of B1, we need to use this angle. For example, let me call it theta 1. So how can we find theta 1? We can use, for example, tangent, or you can use any other function, sine, cosine. At this point, we know enough. I will use tangent. Tangent of this angle, its opposite side, which is CB, divided by adjacent OC. Right? But of course, you can see immediately the angle is 45 degrees. I just wanted to show all the steps. But it's obviously 45 degrees. All right, so it will be CB divided by OC. And of course, theta 1 equals to 45 degrees. Okay, so now components. Let's find component X component and Y component. So it will be B1X. Of course, it will be this component, so you need to project it to this axis. So it will be this component along x-axis. So you need to use cosine function because we are finding side which is adjacent to the chosen angle. So it will be B1 times cosine of 45 degrees. And is this component positive or negative? Since this component points in the positive x direction, it must be positive, and that's what I wrote, right? So it will be B1 times 1 over square root of 2 cosine of 45 degrees, right? Okay, now what about y component? B1 times, of course, now we need to find the opposite side, opposite to the given angle, right? So it's on this side, CB basically, right? So it will be sine of 45 degrees. And what do we have to put here? Minus. Because that component points, you see, component of B1 will point in the negative y direction. You remember, again, the beginning of the semester, I bugged you about that at that point. At this point, you should be aware of that. Should be aware of that. So it's minus. So it will be minus B1 times square root of 1 divided by square root of 2. So we found components. Now let's do exactly the same. Okay, not exactly the same for B2. So B2 equals mu naught I2 divided by 2 pi R2. And again, as I said a few minutes ago, since currents are the same in absolute value in magnitude, right? And R2 equals to R1, so magnitude of B2 and magnitude of B1 will be the same. So, but anyway, let me show it. R2 equals, it's at this distance R2 OA. OB. Yeah, it's OB. And of course, it will be again equals to square root of 2 times 10 to the power of minus 2 meters. And I can write that it's equals to R1. Right? Okay. And over here, I can also write that B2 will be equal to, in absolute value, to B1. Right? Just to emphasize that everything is lots of symmetry. Right. Okay, and now let's find components. Let's write down components. So it will be B2x. B2x, of course, we have to find angle theta 2, but it will be again 45 degrees. Right, I can write here theta 2 equals also 45 degrees. Right. Right, and x component, again, it will be positive in the positive x direction, right? So B2 that way, so x component will be positive. So it will be B2 times cosine of theta 2, which is B2 times 1 over square root of 2. Cosine of 45 degrees, so just remember it's 1 over square root of 2. And y component. Y component, it's that way, up, right? In a positive y direction, so it must be positive. And sine of theta 2 must be used, of course, right? So it will be B2 times sine of theta 2. Okay, let me hold you for extra 2 minutes, guys, right? Yes, basically we're almost done, right? We just need to add corresponding components, that's it. So it will be B2 times 1 over square root of 2, right? Okay, so now finally, first I will write over here. So of course B equals to B1 plus B2. Right, it's in a vector form, but of course we have to add components to write this explicitly, right? So B x component, of course, it will be B1x plus B2x. B1x, B1 times square root divided by square root of 2. B1 divided by square root of 2. And B2x, also, they both positive, right? Plus B2 divided by square root of 2, right? And again, B1 equals to B2. Don't forget, so B1 equals to B2, right? So you can easily calculate, because here, as I said, you can easily calculate here the magnitude, right? I didn't do it. And it will be equal to, I will just use my notes. Actually, I did calculate this B2 and B1, so let me write that down. Where is it? Here. Square root of 2 times 10 to the power of minus 4 Tesla. Right, okay. So that you can compare if you try to calculate. So now, if you take this, plug it here, you will end up with 2 times 10 to the power of minus 4 Tesla. And now y component, but you can see immediately that y component will be 0 because you have, minus, right? So it will be minus b1 divided by square root of 2 and plus b2 divided by square root of 2. And this will be equal to 0, right? So of course we can write in a vector form if you want. B will be equal to x component is that, and then y component is 0. Right. So that's how I would do it, right? Of course, then part B, you need to find magnetic field at point C, but it's way easier because in that case, both B1 will be that way in along x direction, B2 will be also along the same x direction, so you just find these magnitudes and add them up. Find magnetic field at point 2, it will be the same as at point 0, but B2 will be that way, B1 will be that way, so you'll have to repeat exactly the same, very similar steps, but direction slightly different, but logic will be exactly the same.